For years, three-dimensional printing was stuck on tiny houses and cute prototypes. Nothing serious, nothing tall. Then China quietly changed the game. Engineers there have begun a project aimed at printing skyscrapers, towers that usually take an army of workers and years of hard labor. And if they pull this off, it will not just speed up construction, it could flip the entire global building industry on its head. China's first steps toward 3D printed towers. China has started a national test path to push three-dimensional printing from small houses and show pieces toward very tall buildings. Here's how three-dimensional printing in construction works. Imagine a large metal frame or robot arm beside a slab. At the tip sits a nozzle like the end of a giant icing bag. A pump feeds a thick, fast-setting concrete mix into that nozzle. Guided by a digital drawing, the nozzle moves back and forth and slowly squeezes out wet material in strips, stacking one layer on another until a wall stands up. Instead of laying bricks by hand or building wooden molds and pouring concrete into them, the machine shapes the walls directly. China's first big wow moment with this method came when a company called Winsun, also known as Yingchuang building technique, set up a huge printer on an industrial site near Shanghai.
This machine does the work of several construction workers. It lays down the concrete in layers and can build 4 square meters of wall per hour.
In 2014, Winsun printed and assembled 10 small single-story houses in under one day, using a concrete-like ink that mixed cement with recycled construction waste. There were rows of box-shaped homes, each roughly the size of a modest city apartment, but made from stacked printed panels instead of brickwork. Reports at the time said each printed house cost only a few thousand United States dollars, with lower labor needs and less raw material than a normal urban home.
This is significant improvement in evolving a housing market that has the ability to change over time.
Winsun then pushed higher. In Suzhou Industrial Park in Jiangsu Province, it printed a multi-story apartment block about 5 floors tall and a big villa with a floor area of around 11,000 square feet. The printer again made large wall and floor units from a mix of cement, glass fiber, steel, and recycled waste, and crews then lifted those pieces into place. From outside, the apartment block looked surprisingly normal, with stacked balconies and windows, while the villa used curving walls and ornament to show how free-flowing printed forms could be. Engineers at the launch said the structures met ordinary concrete building rules, and contracts were announced for printed villas and houses in other countries.
This construction site, there's no hammering or sawing, just a nozzle squirting out concrete.
Even though workers still had to use cranes and crews to put the pieces together in the yard, the point was clear. Printed parts could be used to build mid-rise buildings, not just small sheds. Another Chinese firm, Huashang Tengda, took a different path and printed a 2-story villa on site in the Tongzhou district on the edge of Beijing. The team first set up a steel frame, plumbing pipes, and a rebar cage where the house would sit. Then a large printer moved around that skeleton and wrapped it in concrete, building up very thick walls in layers. The finished home spreads over roughly 4,300 square feet across its 2 levels and was printed in about 45 working days. Huashang Tengda said it used about 20 tons of strong but cheap concrete, and later reports claimed the villa could survive an earthquake of roughly magnitude 8. In a country with many earthquake-prone areas, the idea that a printed concrete villa could survive a shock like that got a lot of attention. It also showed an important advantage of printing. It can wrap steel, pipes, and insulation inside one thick, continuous wall, which could lead to stronger, disaster-ready homes. By this stage, printed projects in China were no longer limited to walls and houses. Teams also began to use printing for full-scale pedestrian bridges. In Shanghai's Putuo district, builders created a 3-dimensional printed footbridge a little over 50 feet long and about 12 feet wide, made from polymer segments that were printed in a factory and joined together over a canal.
The bridge was created in one facility and then transported into different blocks on site. And on site we assembled it together and then we just picked it up and put it into place.
In the coastal city of Quanzhou, another printed bridge stretched roughly 57 feet from bank to bank and rose about 10 feet from the waterline to the handrail. Both bridges handle real foot traffic. The most ambitious early bridge is in Chengdu. It is about 220 feet long, and the middle section, about 70 feet, is made from a three-dimensional printed polymer. That printed core is attached to normal bridge parts to complete the crossing. Printed pieces this large have passed safety tests, been open to the public, and still carry the weight of everyday traffic. Once people had walked safely across printed bridges, it became much easier to picture printed parts doing serious work inside a tall building. You could start to imagine printed cores, printed beams, and printed support arms holding up real floors. But houses, villas, and one-off bridges are still mostly one company, one team, one moment. They prove that the idea works, but they do not give you a long, careful record that others can trust. China's next step was to move past showpieces and build a formal test building, set up from day. One is a place to study large-scale three-dimensional printing in real lived-in spaces. That test building is a small but important two-story structure, often called the Three-Dimensional Printing Science and Technology Demonstration Building. It was put up by Shanghai Construction Group under a major national research program and is described as China's first fully integrated, habitable, and ready-to-use two-story building that was three-dimensionally printed directly on site. On paper, it looks modest. The total floor area is a little under 600 square feet, and the roof is only about 20 feet above the ground. The key detail is how it was made. The main walls and other load-carrying parts were printed in place by a construction printer instead of being poured into temporary molds the old way. Inside, it feels like a normal small office or living block. There are proper doors and windows, finished floors, lighting, and basic services. To most visitors, it does not scream test building. The difference is hidden in the walls and in the systems watching them. Researchers have fitted the structure with sensors and use it as a long-term lab. Over time, they add weight to the floors and take it away, track small movements in the walls, record where tiny cracks form, and then compare all of that to similar buildings made with standard concrete work. In their papers and reports, the teams behind this building talk about it as a first step toward large-scale three-dimensional printing without size limits. In simple terms, they want the same basic method that can print a two-story, roughly 20-foot-high test block today to grow into a method that can handle much taller towers and more complex pieces of infrastructure tomorrow. By showing that a fully printed, code-compliant, lived-in building can be delivered inside a national research program and watched for years, they are building the base of evidence needed before anyone will accept true high-rise printed structures. Those early wins were the warm-up. The real test begins when you look inside the tools and materials needed to print something as heavy as a skyscraper. The tech China needs to print a skyscraper. Printing a small one-story house with concrete is already a big step. Printing a tall tower is a different kind of fight. In a short house, the walls only carry the roof and maybe one extra floor. In a skyscraper, the lower walls and cores hold the weight of many floors, plus the push of strong winds, plus shaking from earthquakes. Because of all that pressure, the material cannot just look smooth when it comes out of the nozzle. It has to stay strong and stable for decades while holding up everything above it. Engineers in China simplify the challenge into three basic questions. First, can the wet concrete travel through hoses and nozzles without clogging and still come out in a clean, steady line? Second, when each new line lands on the one below it, do they bond into one solid piece? Or do they stay like slices of bread that could slide apart later? Third, how can steel bars, cables, and other reinforcements be placed inside the printed shapes so the final structure acts like the tough reinforced concrete used in normal high-rise buildings? If those three issues are not solved, no one will risk stacking printed walls up to skyscraper height. On the hardware and material side, one of the best examples in China is the team behind Nanjing Kenyo Precision Machine Manufacture and its sister company Jiayi Digitization. Their whole business is based on large construction printers that run on rails or sit inside big gantry frames. A digital model of the building is cut into print paths, and the nozzle follows those paths, laying down concrete in thick, stacked lines. Instead of relying only on fresh sand and gravel, their concrete often uses recycled construction and industrial waste that has been crushed and cleaned into new aggregate. One news report from the company even showed a simple printed bus stop in Nanjing that used about 10 tons of crushed construction waste for just one shelter. That bus stop may seem small, but the real story is the system behind it.
This bus stop is mainly made of construction waste. the process waste was converted into the printing materials.
Kenyo works as a full industry chain company. It designs and builds the printers, creates the concrete mixes that run through those printers, and operates recycling centers that turn broken concrete and bricks into new material for printing. Because one group controls the machines, the mix, and the digital setup, engineers can tune everything together. They can adjust pump speed, nozzle size, and mix recipe as one system instead of guessing which part caused a clog or a crack. High-rise buildings leave no room for error. And if you want to print parts for structures like that, this level of tight control is what helps you reach the strength and consistency people expect from factory-made concrete parts. Nanjing Kenyo and its research partners also show how the technology now goes beyond one or two showpieces. Their site includes projects like curved sound barrier walls along high-speed roads, printed bridge fences, and houses printed directly on the slab with the machine moving around the site instead of staying inside a factory. All of these depend on printers that can run for long hours without drifting off path and on concrete mixes that behave the same way every single day. That is exactly the kind of discipline needed before anyone will trust these machines with key parts of a tall building, such as elevator cores or thick shear walls that handle wind loads. If Nanjing's printers and waste-based mixes show what a commercial setup looks like, a farmhouse in Hebei province shows how far the research side has already gone. In Wujiazhuang village near Zhangjiakou, Professor Xu Weiguo from Tsinghua University and his partners rebuilt a farmer's home as a printed concrete house. The house has 3 bedrooms, a kitchen, a bathroom, vaulted ceilings, and concrete outer walls with a woven pattern. The floor area is about 106 square meters, roughly 1,140 square feet, so it is a full-size rural home, not a small hut. At the site, large robotic arms sat on mobile platforms and slowly stacked wet concrete, layer by layer, to form the foundations and walls. The arched roof pieces were printed separately along a track and then lifted into place with a crane after they hardened. Local and international reports pointed out the same unusual detail. Each printer only needed about 2 people to oversee it, and after pressing a few buttons, the machines kept working on their own without a big crew mixing and carrying materials. The main printing work for the house was completed in about 2 weeks. For skyscraper plans, the important part is not the size of the farmhouse. It is the fact that big robotic arms, working in a normal village, were able to print full walls and complex curved ceilings with very little manual help. Behind that farmhouse is a detailed, design-to-printing workflow that goes far beyond drawing a simple shape on a computer. A research paper on the Wujiazhuang project explains how the team built digital models that included structure, plumbing, electrical routes, and decoration in one file. They then used that same model to plan the print paths, set the robot's speed, and schedule each step of the job. According to the authors, this approach cut on-site labor by more than half compared with a normal reinforced concrete house, and reduced the total construction time by about 1/4. In simple terms, the robots were not just gadgets. They were part of a full system that saved real time and real work on an actual building. Once you have the machines and digital planning in place, the next question is what goes inside the hose. 3-dimensional printed concrete has to pass 3 tests at the same time. It must flow smoothly through pumps and hoses without blocking them. It must be stiff enough when it comes out so that each new layer does not squash the one below it. And after a few hours and days, it has to harden into something with high strength, just like good structural concrete. Reviews of printable concrete mixes show how researchers in China and other countries adjust the water level, cement type, fine aggregate size, and chemical additives until the fresh mix acts almost like thick toothpaste coming out of the nozzle, but still sets fast enough to hold more layers on top. Layer bonding is another small detail that becomes a serious problem if it is ignored. When the printer stops and starts or waits too long between layers, the top surface can dry out. If the next layer is placed on top like cold glue on a dusty wall, that joint becomes a weak spot where cracks can start. Lab tests in recent papers show several ways to keep these joints strong: lightly roughening the top of older layers, limiting how long the machine pauses before adding the next line, or adjusting the mix so the fresh paste softens the surface below and ties into it. Even if bonding is perfect, printed concrete alone is not enough for the heavy loads in high-rise buildings. That is where reinforcement comes in. One Chinese research group has tested beams and wall panels where three-dimensional printed parts act as permanent formwork. They print hollow shells with ribs and cavities, place steel bars inside those cavities, and then fill them with normal cast concrete. When these test beams are pushed until they crack, their bending strength is similar to, and sometimes slightly higher than, traditional beams of the same size made with standard formwork. For tall buildings, this idea is very appealing. The printed shell gives the exact shape and cuts down on wood and labor, while the steel and cast concrete inside provide the proven strength that engineers already trust. Other tests look at how printed walls handle earthquakes. Instead of printing only straight, solid walls, some teams combine printed cores with stronger frames or borders built in more traditional ways. In one widely reported study, a small house-like structure with printed walls and special frames was placed on a shaking table and shaken with motions equal to strong earthquakes. The walls developed cracks in controlled areas, but the structure did not collapse. This suggests that properly designed printed walls can work inside seismic systems rather than act as weak points. For any future printed tower, this kind of result is vital because wind and quake forces usually decide how the main vertical structure is designed. To make all of this work, the control systems inside the printers must be far smarter than a simple concrete pump. In projects like the Wujiazhuang farmhouse, the mobile platform of robotic concrete printing includes a robotic arm, a lift, and a platform that drags mixers, pumps, and control cabinets along with it. Software slices the building model into thousands of thin layers and turns each layer into a path for the nozzle. The machine has to match arm motion, pump speed, and nozzle opening, so every printed line stays the same width and height. If the arm moves too fast or the pump slows down, the printed line becomes too thin, and small errors can stack up over many feet of height. That is why Chinese research teams spend so much effort on calibration and on sensor feedback that tracks nozzle position, pressure, and even the temperature and humidity around the print. But even if the tech works, why does printing a skyscraper matter for China in the first place? The real reasons China wants 3D printed skyscrapers. China's rapid growth in tall buildings is the main reason a three-dimensional printed skyscraper would matter at all. Over the past 2 decades, China has filled its major cities with high-rise towers faster than any other country. An international database shows that by the middle of 2023, the world had about 2,086 buildings taller than roughly 650 feet, or 200 meters. About 1,041 of those towers were in China. More than half of all buildings in that height range were completed after around 2015, and China has led that surge every year. Each of these towers is made from huge amounts of concrete, steel, glass, and interior materials that must all be mixed, moved, and installed. When this activity happens nationwide, it becomes a system-wide problem. It creates massive piles of leftover debris, high emissions from making so much cement, and long seasons of hard manual work for millions of workers. Any real three-dimensional printed high-rise will be judged by whether it can ease these pressures, not just by whether it looks futuristic. One of the biggest pressure points is construction and demolition waste. This includes broken bricks, concrete chunks, plaster, tile, and other scraps from building and tearing down structures. Researchers tracking these flows in China estimate that the country produces about 2.4 to 2.6 billion tons of this waste every year, far more than the total weight of its household trash. Several studies also say that construction and demolition waste makes up between about 30 and 40% of all solid waste generated in the country. Most of this debris is still taken to landfills or dumped in low areas on the edge of cities. Academic reviews say only a small amount is actually recycled, with national recovery rates often estimated at only about 5 to 10%. This is far behind countries that recycle more than 90%, and it means every new tower adds to old piles of waste. Traditional high-rise building methods make the problem even worse. Casting concrete on site means putting up temporary wooden or metal molds, pouring the wet concrete, and then removing all the molds once it hardens. On busy tower sites, formwork gets bent, cut, and broken, and scraps from rebar, bricks, blocks, and panels end up in dumpsters. When old buildings are torn down to make space for new towers, demolition adds another wave of rubble. The same boom that built China's modern skyline has also created waste streams that are hard to manage. Three-dimensional concrete printing is interesting because it puts material only where it is needed. Instead of pouring full solid walls and cutting them to size, a printer places fresh concrete along exact paths. There is no formwork to build or throw away. Reviews of three-dimensional concrete printing say that by removing formwork and reducing scrap, this method can cut construction waste by about 30 to 60% compared with traditional building, while also speeding up the job. For China, there is another key link. Several recent research papers on concrete printing talk about mixes that replace a large part of the sand and gravel with crushed construction waste. In ordinary concrete, that sand and gravel layer is called aggregate. Instead of hauling broken concrete to a dump, it can be sorted, crushed, and fed back into new printed walls as aggregate. Because printed elements are made layer by layer under tight control, it is easier to keep the quality of this recycled aggregate within a safe range. In older districts where mid-rise blocks are being torn down and replaced by taller towers, rubble from older buildings could become part of the material for new printed cores and walls without ever leaving the city. Behind the waste problem sits the bigger question of cement and emissions. Concrete is mostly sand and stone, but the powder that glues it together is cement, and making cement is very energy-intensive. To make ordinary Portland cement, producers heat limestone and other materials in huge kilns until the rock breaks down and releases carbon dioxide. Global studies say that cement production is responsible for around 8% of all human-made carbon dioxide emissions each year, which makes it one of the largest single industrial sources. Because China has built so much in such a short time, its share of this impact is huge. In 2010, for example, researchers estimate that China produced roughly 1.9 billion tons of cement, which was about 56% of the world total that year. Since then, China has remained above half of global cement production, and its cement sector alone now emits hundreds of millions of tons of carbon dioxide every year. That means the way China builds and rebuilds its cities is central to whether it can cut its climate impact. Three-dimensional concrete printing will not remove these emissions completely, but it does give builders direct ways to reduce them. Printed structural parts can be hollow or have ribs inside, so they carry the same loads while using less material. That means less cement per floor. Printed mixes can also replace part of the cement with other binders, including certain industrial byproducts from steel or power plants. And when printing uses recycled aggregate from construction and demolition waste, the need for fresh sand and stone also goes down. When even small percentage savings per building are multiplied across hundreds or thousands of high-rise projects over many decades, the total reduction can reach many millions of tons of avoided emissions and saved raw material. These issues show up in the daily work of people on construction sites. For years, China's building boom has depended on migrant workers who leave rural areas to take some of the hardest and most dangerous jobs. Studies of China's labor market say construction involves long hours, tough conditions, and growing safety concerns, and younger workers are less willing to stay in these roles. At the same time, China's workforce is aging, and many older workers who helped build the last wave of towers are nearing retirement. Safety research makes the human cost clear and links it directly to tall buildings. Analyses of accident data in China show that migrant workers face higher risks than non-migrant workers, with one study finding that the severity of accidents for migrant workers was more than 2 percentage points higher. Reviews list falls from height, getting struck by falling objects, and the collapse of temporary structures as common causes of death and serious injury, especially on high-rise sites with scaffolding, tower cranes, and partly finished floors. A move toward three-dimensional printed high-rise structures would significantly cut down on these dangers. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.